Hello everyone, welcome back to Must Electronics. Today we will learn how to interface the STM32 with the MPU6050, which is a popular low-cost microchip that combines a 3-axis accelerometer and a 3-axis gyroscope to track linear acceleration, tilt, and rotational motion for microcontrollers like STM32 Arduino. And then in the next video, we'll do a small project by controlling LED patterns by hand gesture using this same setup. Let's go through the components needed. BlackPill, which is STM32F411CEU6, MPU6050, Nucleo, jumper wires, mini USB cable, PCB, 5-volt regulator, bulk strip, wires. Here you can see the connection between BlackPill and MPU6050. Let's start the hardware connection. For flashing, you can follow this. That's all for the hardware. Now it's coding time. Open STM32 Cube IDE. If you have not used this software before, we have already covered this topic in how to interface OLED display with STM32 video. Link is available in the description below. Please have a look into that. Go to File, New, STM32 Project. Select STM32F411CEU6. Click Next. Enter the project name. Click Finish. Since the MPU6050 communicates via I2C, configure PB10 as I2C2 SCL and PB3 as I2C2 SDA. Now we need to enable I2C2. For that, go to Connectivity, click on I2C2, Enable. Leave rest of the configuration as is. Save the file. The code will be generated automatically. The code is already available on GitHub. The link is in the description below. Download and unzip the project. Here you can find both BlackPill MPU6050 interface code and LED pattern code. First we will do BlackPill MPU6050 interface. You can also find circuit diagram here. We will be working entirely inside main.c. That's the only file we need to modify. I'll replace the entire content of the default main.c with our code and then walk you through exactly what we have written and why. Alright, so here is our complete main.c file. As you can see, a large portion of this is auto-generated by STM32 Cube IDE. Things like the file header, the system clock configuration, GPU and I2C initialization, and the error handler. We don't need to touch any of that. What we care about are the parts we have written, and I'll point those out clearly as we go. The first thing we have added is right here in the private define section. We define the I2C address of the MPU6050 as 0xD0. Now the MPU6050's 7-bit address is 0x68. That's the default when the AD0 pin is pulled low. But STM32's HAL library expects the address in 8-bit format, which means we shift it left by 1 bit, giving us 0xD0. So keep that in mind. Whenever you see MPU6050 addresses mentioned in datasheets, they are usually in 7-bit format. But here we use the 8-bit version. Next, in the private variable section, we have declared all the variables we will need. These 6 variables hold the raw 16-bit integer values directly read from the MPU6050 registers, 3 for accelerometer access and 3 for gyroscope access. These 6 float variables will hold the processed human readable values, acceleration in g and angular velocity in degrees per second. And finally, 2 status variables. Check variable will store the OIM register value that we read from MPU6050 to verify the device is connected and responding correctly. MPU init success variable is a simple flag. It will be set to 1 if initialization succeeds, or remains 0 if something goes wrong. In function prototype section, we have declared the three functions we are going to write. One for initializing the sensor, one for reading the accelerometer, and one for reading the gyroscope. Simple and clean. Now let's look at the first and most important function, MPU6050 init. We start with a 100 millisecond delay. This gives the MPU6050 enough time to power up and stabilize before we try to communicate with it. Next we read from register 0x75. That's the Who I Am register. This register always returns the fixed value 0x68 for the MPU6050. So if the I2C communication fails, or if the value we get back is not 0x68, we know something is wrong. We set MPU init success variable to 0 and return early. No point continuing the setup. If everything checks out, we set MPU init success variable to 1 and carry on. This line writes 0x002 register 0x6b. That's the power management register. By default, the MPU 6050 starts in sleep mode. Writing 0 here wakes it up and sets it to use the internal 8 MHz oscillator. We also add a small 10 millisecond delay after waking it up. Register 0x19 is the sample rate divider. Writing 0x07 here sets the sample rate to 1 kHz divided by 1 plus 7, which gives us 125 Hz. That's plenty fast for most applications. Register 0x1b is gyro config. Writing 0x00 sets the gyroscope full scale range to plus or minus 250 degrees per second, the most sensitive setting. Register 0x1c is accelerometer config. Writing 0x00 sets the accelerometer full scale range to plus or minus 2G, again the most sensitive setting. We finish with a 50 millisecond delay to let the sensor settle after configuration. Now let's look at MPU6050 read accel. We declare a 6 byte buffer called REC data. Then we will read HL I2C memory to read 6 bytes starting from register 0x3b, which is accel X out H. The MPU6050 stores each access value as a 16-bit signed integer split across two consecutive registers. High byte first, then low byte. So 6 bytes gives us all three access. If read fails, we return immediately. Here we combine the high byte and low byte for each axis using a left shift and bitwise OR. The result is cast to int64t to get a proper signed 16-bit integer. Finally, we convert the raw values into acceleration in G. Since we configured the full scale range as plus or minus 2G, the sensitivity is 16384 LSB per G as mentioned in MPU6050 datasheet. So we simply divide the raw value by 16384 to get our final result in G. The MPU6050 read gyro function follows the exact same pattern. We read 6 bytes starting from register 0x43, which is gyro X out H. We combine the high and low bytes the same way to get the raw 16-bit values. And we convert to degrees per second by dividing by 131. This sensitivity value, 131 LSB per degree per second, comes directly from the datasheet for the plus or minus 250 dps full scale setting that we configured. Now let's look at the main function. Most of it is auto-generated. HAL init, system clock config, MX GPIO init, MX I2C2 init, all handled for us. The two things we have added are MPU6050 init, right after peripheral initialization. We call MPU6050 init to set up and verify the sensor before entering the main loop. And inside the infinite loop, we continuously call MPU6050 read accel and MPU6050 gyro to keep updating our data variables with a 300 millisecond delay between each read. That's roughly 3 readings per second. good enough to observe and debug the values. Alright, the code is ready. Let's flash it onto the BlackPill and see it in action. I have soldered between Nucleo and BlackPill as the jumper wires were loose. Let me flash now. Let me run it in debug mode. I'll click Run Debug as STM32 application. Once the debugger starts, it will pause at the beginning of main. Before we hit resume, we need to set up our live expressions so we can watch the values in real time. Go to live expressions. Now let's add the variables we want to watch. I'll add AX, AY, AZ for accelerometer, GX, GY, GZ for gyroscope, MPU init success to confirm the sensor initialized correctly. Now let's hit resume and let the code run. First thing to check, look at MPU init success. It's showing 1. Perfect. That means the MPU 6050 was detected successfully on the I2C bus and all the configuration was applied without any issues. If you ever see a 0 here, double check your wiring and your I2C address. You can see AX and AY are close to 0 and AZ is close to 1. This makes perfectly sense. When the sensor is flat and still, it's only feeling gravity pulling straight down, which is the Z axis. So AZ reads approximately 1G and the other two axes read nearly 0. The gyroscope values Gx, Gy, Gz are all hovering around 0 as well because the sensor is not rotating. Now let me tilt the board. I'll rotate it so it's standing up on one edge. Watch what happens. AZ drops and either AX or AY increases depending on which direction I tilted it. Gravity is no longer aligned with the Z axis, so it gets distributed across the axis. If I tilt it roughly 45 degrees, you will see the values split more or less equally between two axes. And if I hold it completely vertical, now AZ is near 0 and one of the other axes is close to 1. The sensor is measuring the full effect of gravity on that axis. Now let's look at the gyroscope. I'll rotate the board slowly. See how one of the Gx, Gy or Gz values jump up while I'm rotating. That's the angular velocity in degrees per second. The faster I rotate, the higher the value. When I stop, it drops back to near 0. The gyroscope measures how fast you are rotating, not the position. So as soon as the movement stops, the reading goes back to 0. Let me also give it a quick shake. Watch the accelerometer value spike. They jump up well above 1G because the sensor is experiencing acceleration from the movement on top of gravity. This is exactly what you would use to detect things like tap detection, free fall, or vibration in a real project. So to summarize what we covered today, we connected MPU 6050 to the BlackPill over I2C, wrote the initialization and data reading code from scratch, and verified everything live using the STM32Cube IDE debugger. You can now read accelerometer and gyroscope values reliably on any STM32 project. In the next video, we are going to take this further and build something really fun, a gesture controlled LED display that you strap to the back of your hand. 4 different LED animation modes, all controlled by how you tilt and shake your hand. If this video is useful, please like the video and subscribe to Must Electronics.